Hello everybody, today I'm going to talk about interference due to reflected light rays from the thin film. So in the previous class, in the last class, I have told you we have discussed about what is thin film and how we get the interference due to thin films. And today we are going to talk about the interference due to reflected light, and that reflected light from a thin film. So let's get started. So I have a thin film. This is my thin film having thickness T, and the refractive index of the material of the thin film is mu. Okay, now I'm incidenting a monochromatic light source. Monochromatic means what? A single wavelength light is incidenting on the thin film with incidence angle I. So with the reference of normal, I'm taking the angle. The incident angle is I. This is the normal. So the incident ray, I'm calling it as A B, and from here we know that because the light is hitting a medium, there is a boundary. This, due to this boundary, the part of this incident light ray will get reflection from the top surface of the thin film with the angle I, because actually this is the reflection angle, but we know angle of incidence is equals to the angle of reflection. That's why this is also I, and I am calling it as this point as C, and this is my reflected part of this incident ray. And there will be one more part from this incident ray, that will be the transmitted ray. The remaining amount of the light will transmit. Actually this is the original path, but because of this boundary between these two different mediums, the light will suffer a deviation, a slight bend towards the normal, because it is traveling from a rarer medium to the denser medium. So that's why the transmitted light will bend slightly towards the normal. So this is the transmitted ray. So I've got a ray which got reflected from the top surface of a thin film. Now again, this transmitted ray will reflect. This is, so from here, this is the angle of refraction, calling it as R. So from here we see this, due to this bottom surface of the thin film, the ray, this transmitted ray will, the part of this transmitted ray will again suffer a reflection, and a part of it will transmit and will come out of the thin film. And same again, because the light ray is traveling from denser to rarer, the reverse of it will happen. Initially the light got bent towards the normal. Now the situation is different. The medium, the boundary is, the traveling is from denser to rarer, the light will bend away from the normal. So I'm giving naming for them. So this is my AB as incident ray, and my BC is the reflected ray, and again this transmitted ray, here I'm calling it as F, and again I'll call this as T, and this reflected ray from the bottom surface of the thin film will hit this top surface of the thin film, and again the same phenomena, part of this reflected ray from the bottom will suffer transmission, and part of it will again reflect from the top surface of the thin film. So this is my normal. Saying that light is traveling from denser to rarer, it will bend away from the normal. likewise. So here I'm calling this as D. This is just for denser medium I've rolled. Now this point is a D. D to E is another reflected light. Actually this light ray, some people will get confused. They'll say that this is the transmitted ray because this one is the reflected ray. This is the transmitted. Yes, you're right, but we are talking about reflection from the bottom surface of the thin film. So actually they both are the reflected rays. The one from the top surface of the thin film, the other from the bottom surface of the thin film. So the both are reflected rays only. And the thickness of the thin film is constant throughout. That's why these two light rays, these two reflected light rays, I'm calling them as R1 and R2, are exactly parallel to each other. If the thickness would have been something different, then you won't get the parallel light rays, the parallel reflected light rays. Why you got the symmetry, the exact parallel light rays, parallel reflected light rays? It is because of the constant thickness of the thin film. And now the naming, I will be using this point for the geometrical calculation of the distance. So this is my not used G. This is my point G. Okay, and now I'm giving the angle to this particular this. So you see, this is my R. So what this can be? This can be also R. How come? Because this normal is exactly parallel to this normal, so that's how this angle will be equal to this angle. It means this is also R, that is for sure. So from that we know the angle of incidence is equal to the angle of reflection. Similarly like this, so here we can also write this angle as R. Why? Because this is the incident angle and this is the reflected angle. If incident angle is R, then reflected angle is also going to be R. Okay. Now one more thing. Everything is done. Now what we have done, so you see we have created the thin film, actually have created a coherent source using a single source, that is this source. The thin film has created two light sources which are having the same wavelength, same frequency, and having the constant phase difference between them. If two light rays are having these properties, what we call them? We call them as coherent source. If you have the coherent source, yes, exactly, we can have the interference pattern. So with the help of these two light rays, we will get the interference pattern. And one more question arises is that two parallel rays won't meet, they will meet at infinity. So how come we can see the interference due to this R1 and R2? That is, with the help of an eyepiece or microscope, or if you don't have those things, if you're directly viewing with your naked eye, your eyeball, your convex eyeball will help you to merge, to interfere these light rays, and you will see the interference directly with your eye. Okay, now this type of interference is the division of amplitude. Why we are calling it as division of amplitude interference? Because initially the wave will have some amplitude. The amplitude won't be same exact, the similar amplitude you will not get to the reflected and to the transmitted rays. The amplitude will decrease. If you sum them up, you will get the amplitude of the incident ray only. That is the idea. Splitting of amplitudes. That's how you're getting the two waves. Okay, and again here, this wave will also have, it won't be exactly same with this amplitude, and this amplitude won't be exactly same. The ray 2's amplitude will be bit lesser as compared to the ray 1's amplitude. Okay, even then they will interfere. Now we will find out the path difference between the ray 1 and the ray 2. Why we want to find out the path difference between them? Because with the help of the path difference, we can find out the condition for the bright fringe and the condition for the dark fringe. Same as we did for the Fresnel biprism, Young double slit experiment, we got the condition for the bright fringe and the dark fringe. The condition means what? It will tell you what should be the path difference so that you can get a constructive fringe. What should be the path difference so that you can get the destructive fringe. So similarly, here we will find out the condition to get a bright means the path difference for the constructive interference or the bright fringe, and the path difference for the dark fringe or destructive interference. So let's get started. For that, we have to find out the path difference between these two rays. So for that, I have to draw a perpendicular, and this point I am calling it as H, a perpendicular to the ray 1, and I am calling this point as H. So I need to know this angle. What is this angle? So from the geometry, we can see that if this is I, because these two rays are exactly parallel to each other, and this is the normal, and these two rays are exactly parallel to each other. If this is I, this is also I, this angle is also I, and we know that this thing is 90. So 90 plus I, and if I take it something like this is also 90. What remains is my I only. So it means the triangle BHD is having angle I. Okay. Now we will find out the path difference between these two rays. The story is same, exactly same. After this particular point, they will travel exactly same distance. Even if they travel for 1 kilometer, 2 kilometers, or 1000 kilometers, any distance that is, they will travel exactly same distance. If I just talk about these 2 points as starting points, the story is before these 2 points. The story lies in here, this area. You see, the ray 2 has traveled a bit bigger distance as compared to the ray 1. The ray 1 has traveled the small distance, this only, but the ray 2 has traveled this plus this distance. So what I have to do, I have to find out these two distances, I have to add them, and I have to subtract the distance from this distance. Then I will get the path difference between the ray 1 and the ray 2. So let's do it. So before, I have to do the geometrical path difference first. So the geometrical path difference will be without considering the medium, in which medium the light ray is moving. We won't consider the medium. Without considering, we will find out the path difference. That path difference we will call it as geometrical path difference. So the geometrical path difference will be is BF, this distance I have to add with this distance, that is FD plus FD minus, I have to subtract this short distance, that is BH. What I'll get? I'll get the path difference between the ray 1 and the ray 2. This is the geometrical path difference. The optical path difference will be there in while considering the optical path difference, optical path difference, in this calculation we will take into account the medium also, the refractive index of the medium also. Okay, so here we will multiply the medium with the distance traveled by the light in that medium. So for that, this distance the light has traveled in the thin film who is having the refractive index mu. So I have to multiply mu with BF plus FD minus the refractive index of the air. We will take it as 1. So that is how it will be what? BH. So this is the optical path difference. Now I have to find out the values of these unknown quantities, these unknown things, the distance of BF, FD and BH. Using the geometry, using the trigonometry, we are going to do that. Now, first we will find out. So from the from the geometry of the figure, there are some simple calculation, there are some similar distances. Those are, you see, I am taking this triangle, the triangle BD. So this is F and here's the G. So this triangle, this one is having R and this is also having the angle R. So what I am claiming is that the distance BF is equals to the distance FD. Why? Because they both are having the same angle. If this angle would have been a bit bigger, likewise, so it won't be equal. You see, now you can see this distance is bit longer than this distance. Why? Because this angle is greater. If the angles are same, we can equate the distances. This distance is equals to this distance. Okay, so from that I can write it as 2BF because BF is equals to FD. So I can write it as 2 mu BF minus BH. Are you getting my point? Now I have to find out the value of BF. In which triangle BF is coming? BF is coming in the triangle BGF. So from the triangle BGF, this triangle, here's I am having G, B, F. The angle is R. So from this triangle, cos R is equals to adjacent by hypotenuse. What is my adjacent? This is my adjacent, that is GF divided by hypo. This is my hypo. What is that? BF. So I need to know the value of BF. So I'm taking it in one side. This BF is equals to, what is the value of GF? GF is the distance, is the thickness of the thin film. G to F is the thickness of thin film. That is what it is. It is T. So instead of GF, I can write T. So T by this thing, R, cos R. So I got the value of BF. Now there is one more unknown thing, that is BH. Now I have to find out the value of, what is the value of BH. To find out the value of BH, I will do some, so before finding the value of BH distance, I'll do some simplification. you just have a look at this. The distance BG is equals to GD. Why? Because this angle, the angle is exactly same, means this distance is exactly equal to this distance. So it means BG is equals to GD. So I can write BD can be written as 2BG. Why? Because BG is equals to GD. Now we will be finding the value of BG using the triangle BGF. Using this triangle, tan R is equals to opposite by adjacent. What is opposite from this triangle? It is BG by GF. And we know the GF is the thickness of the thin film. G to F is the thickness of the thin film T. So T tan R is equals to BG. So I got the value of BG. I'll substitute in here. So BD will be equal to 2. What is the value of BG? BG is equals to T tan R. Okay, I got the value of BD, that is equals to 2T tan R. So I will be using this expression, and I'll be using this expression. Now I have to find out this distance, that is BH. BH I want to find out. Now from this triangle, from triangle BHD, the triangle is something like this, 90, angle is I, this is H, here's my B, here's my D, and here's at the center G is there, but I'm not going to use that. Now from that triangle, sine I is equals to opposite. Here's the theta, opposite to the theta will be sine opposite, that is BH, opposite by hypotenuse. Which is the hypotenuse? Hypotenuse is the BD, because this is 90. BD. So I have to find out BH. I'm taking that one side, BD into sine I. What is the value of BD? BD is equals to, from this equation, BD is equals to 2T tan R. 2T tan R. And from Snell's law, sine I is equals to mu sine R. Angle of incidence is equals to sine into the angle of incidence is equals to mu sine into the angle of reflection. So I'll be replacing this sine I with mu sine R. So BH is equals to 2 mu T tan R sine R. I got the value of BH. I have the value of BF. Now the path difference, the optical path difference between the ray 1 and ray 2 is 2 mu, as it is the value of BF. BF is T by cos R minus BH. BH is this thing, 2 mu T tan R sin R. So from here I am taking common 2 mu T by cos R, nothing will be there, 1 will be remaining, minus 2 mu t is gone. This is sine r by cos r. By cos r is gone. Sine r will be there, and there will be one more sine r. So it is gonna be sine square r. So from 1 minus cos square theta is equals to sine square theta. I can write this as cos square r. It will be 2 mu t by cos r cos square r. Square 1, this will get cancelled. The optical path difference is 2 mu t cos r. This is the optical path difference. Optical path difference between the reflected light rays R1 and R2. So the path difference, this is not the true path difference between the ray 1 and ray 2. There will be a one more path difference that will come into picture due to the reflection of light from denser medium. When a light is hitting the denser medium and getting reflect back in this reflect back in the rarer medium, this reflected light will suffer a phase change of pi and the path change and the path difference of lambda by 2. So this is the optical path difference, but there will be a path difference due to the reflection. We have to take into that we have to take that also into account. So the true path difference is equals to 2 mu t cos r. I can take either plus or minus, it doesn't matter. Here I am taking as minus lambda by 2. Here I am talking about path difference, so that's why I'll take lambda by 2. How come we got this lambda by 2? One more time I am explaining. You see, when the light get reflection due to the denser medium, here's the denser medium, the boundary from rarer to denser medium, when the light hits get reflected back, this light ray will suffer the phase change of phi and the path difference of lambda by 2. You can say the same thing as, sir, the light ray is also getting reflected from this surface, so this light ray will also have the phase change of phi and this will also have the phase change of phi. Because they both are getting the same phase change, so the result will be nil. So there will be no difference because they both are getting the phase change. But you see the thing is, it is not just the path difference is not just demanding for the reflection, it is demanding for the reflection from the denser medium. If the reflection is happening due to the denser medium, then only it will suffer a phase change of phi and the path difference of lambda by 2. You see, this ray is suffering reflection, yeah, that is okay, but you see, this reflection is happening due to the boundary of rarer medium. That's why this ray won't have the phase difference and the path difference, phase change and the path difference. That's why this won't get. So this is the true path difference between the ray 1 and the ray 2. Now we will find out what is the condition. Now we will find out what is the condition for what should be the path difference to get the bright fringe or the constructive interference, and what should be the condition for the path difference, what should be the path difference to get a dark fringe or destructive interference. So now we know that the generally maxima, maxima means the bright fringe. Bright fringe condition is the path difference should be n lambda. If the path difference is n lambda, it means we will get a bright fringe. So this is the path difference. I am equating this path difference with n lambda. I will get the condition for the bright fringe. So 2 mu t 2 mu t cos r minus lambda by 2 is equals to n lambda. So 2 mu t cos r is equals to n lambda plus lambda by 2. It will give me n plus half lambda. So this is the path difference to get a constructive interference. But you see, the value, the path difference is not similar as that of which we got in the Fresnel biprism and the Young's double slit experiment. The condition of the path difference to get a bright fringe got flipped. Why? Because of this reflection due to the denser medium. This change is occurring. Generally, this equation, this quantity, this expression represents that you are going to get a dark fringe. But here the condition got flipped. Why? Because of this reflection from denser medium. Initially, in the Young's double slit experiment and Fresnel biprism experiment, we used to get this expression, this path difference expression for destructive interference. But here we are getting it for bright fringe. Okay. Now similarly, we will find out the path difference for destructive interference. Here we did for the bright means constructive interference, bright fringe. Here we will do for dark. Now the path difference condition for dark fringe, the path difference should be n minus half lambda. If this path difference is there, you will get a destructive interference. This thing represents, this path difference will give you destructive interference. Now we will equate this path difference with the true path difference which we got from this experimental setup, that is 2t mu cos r, 2t mu cos r minus lambda by 2 is equals to n minus half into lambda. What we will get? We will get 2t mu cos r is equals to n lambda. You see, in previously we used to get this expression for the path difference to have the constructive, the bright fringe, but here the condition got flipped, as I told you earlier. So this is the path difference to have a dark fringe. Okay, so this was all about interference due to reflected light. Similarly, we can find out, we will get the interference due to the transmitted light rays. So these two transmitted light rays, if I call it as these two transmitted light rays will show you the similar effect as you saw now. Here the reflected light rays are giving you the interference pattern. The similar way the transmitted light rays will merge and they will also give you the interference pattern, and we'll see what is the difference between this interference pattern and that interference pattern. There is a difference, they are not exactly same, there is some difference. We will see what is that difference and how to get the conditions for the dark and bright fringes for the transmitted light rays and how that will work in our next class. So thank you so much, keep watching.